Hello everyone, welcome to day 18 of Advent of Code. Today was very hard, for me. The problem wasn't hard at all and was just a straightforward application of Pick's theorem and the shoelace formula. However, I knew neither of these, so today's video is almost 4 hours of me discovering that trying to solve a computational geometry problem with careful counting is tricky to write, hard to debug, and slow to execute. So, instead of watching, you might want to just read the Wikipedia articles on Pick's theorem and the shoelace formula. Links in the description. As always, this video has chapters so that you can skip around, and the link to the code is also in the description below. Now, without further ado, let's get started. Day 18. Lava Duct Lagoon. Thanks to your efforts, the Machine Parts Factory is one of the first factories up and running since the lava fall came back. However, to catch up with the large backlog of parts requests, the factory will also need a large supply of lava for a while. The elves have already started creating a large lagoon nearby for this purpose. However, they aren't sure the lagoon will be big enough. They've asked you to take a look at the dig plan, your puzzle input. For example, this is something, and these look like colors. The digger starts in a 1 meter cube hole in the ground. They then dig to the specified number of meters up, down, left or right, clearing full 1 meter cubes as they go. So this means right 6 cubes. The directions are given as seen from above, so if up were north, then right would be east, and so on. Each trench is also listed with the color that the edge of that trench should be painted, as a hexadecimal color code. When viewed from above, the above example dig plan would result in the following loop of trench, having been dug out of otherwise ground-level terrain. So we start with right 6. So we start here, presumably, and then we do 6 cubes right, and then 5 cubes down, and then left 2 cubes, and so on. Notably, each edge is actually 1 plus this, since we start in a cube and then make more holes. At this point, the trench could contain 38 cubic meters of lava. However, this is just the edge of the lagoon. The next step is to dig out the interior so that it is 1 meter deep as well. Now the lagoon can contain a much more respectable 62 cubic meters of lava. While the interior is dug out, the edges are also painted according to the color codes in the dig plan. The elves are concerned the lagoon won't be large enough. If they follow their dig plan, how many cubic meters could it hold? Okay, we could just do a flood fill here. Let's look at the puzzle input first. These are a lot of instructions, and the trouble is that we don't know how big the whole grid will be, so we probably don't want to actually draw out. We don't actually want to store the grid as a grid. This feels like it must have some existing algorithm. As in, this feels like it's drawing out multiple convex polygons. It's not even polygons, it's going to be just rectangles. It's drawing out multiple rectangles, and we have to compute. And then we have to compute the space inside of the rectangles. But we can do it even simpler, can't we? We can just do a sort of line scanning thing. As in, we know we can fairly easily compute from our input how many rows we have in total. Because we can just simulate this and see how many rows we have. And we also know the edges. These are going to be edges. And then we can just take each line and see how many spaces are contained in the line. Right, so perhaps the way we do this is we follow the instructions and generate a data structure that represents our grid. But it won't actually be a grid of characters. Instead, what it will be is, it will be a map from line to something else. And the something else for each that we store for each line is going to be the squares, the spaces on that line that are filled in, and their color. This is probably going to screw us over in the second part, but it will at least make computing, so it will at least make solving the first part easy, right? Because if we have, say, for line 1, the fact that we have a square here and a square here, we know the edges, we know the min and the max of this line, obviously. So we can just compute everything in between. Yes, and if there are multiple, if the drawing sort of loops around, we just have to compute segments. So say if there was a hash here, if this space was filled in, then we need to compute the amount of space between the first 2 hashes and then the amount of space between the second 2 hashes. So this is sort of segments. Yes, for each row, we'll be essentially storing segments in a sort of spread out fashion. And our visualization is just going to be drawing this thing. In fact, we can start with our visualization since we just have to follow these instructions. Yes, let's start with our visualization so that we see. Okay, so first off, we're just going to parse this, which is fairly easy. And then we're going to draw out a visualization to see what our full input actually looks like. Let's see how complex of a structure we have. So let's get going. We're solving this in Livebook, so we start by creating a new notebook. Now, in order to do our actual parsing, we're first going to split on spaces, and then we're going to use Elixir's binary pattern matching to remove the parentheses from around the colors. So then we should end up with a list of direction, length, and color. Okay, this, what does the full example look like? All right, it is way more complicated. And it definitely, right, so when we consider this and do it line by line, we'll definitely have to take into account that there will be multiple segments on each line. Right, so let's get to actually coding this up. How do we do that? We are going to compute a map that goes from line to which cells on that line are filled in. Then we're going to go over this map again and count the number of spaces between each segment. For example, if we do this here, we will count these lines here, the space here, the space here, the space here, and so on. So we're only going to do alternate segments. This should work because we always have to start with a filled-in space to get to a segment. Then we always start from the outside. Right? Let's write this. Can I actually add a bit of a border around this first? Okay, and now we have a nice little border. This works on example as well. Yes. Okay. Now let's actually solve part 1. So there are a lot of filled-in spaces on 0, only 2 on 2, right? Only 2. Yeah, then there's going to be only 2 until we get to this line, whatever it is. It's going to be 4, up, then 2, then this is the end. So this is this. So this is this line. We have 0, 1, 2, and 6. 0, 1, 2, and 6. Then it goes all the way down to 6 on the last one. But it's 1 through 6 instead of 0 through 6. Okay, this looks correct. And now I think we want to compute pairs. So what happens if there are multiple filled in like this? Well, if it's an extent, then it doesn't matter. Or if it's a whole line, then it doesn't matter. Because the space here is six filled in slots. And here it's going to be everything between 2 and 6. So it's a bit more complicated than just taking pairs, but not much more complicated. So we have 0 and then 6. The 6. I kind of need a grid. Let's draw a grid. Okay, and now we have a little grid. Is the full example still readable if we do this? The full input. Kinda. This is fine. Okay, now back to our example. It should be 66444. 6, 4. Why did it get 4? Because it actually computed 6 and then 4 instead of 6 and 6. Ah. This is annoying. This is the point where I really wish I knew some computational geometry. Because surely there's an algorithm to compute the surface of a shape like this. But hey, in for a penny, in for a pound. Let's do it like this, and then we see what part 2 is all about, and then maybe we get a better algorithm. So, the problem here is that we're computing this line instead of, we're computing 1, 2, 3, 4, 5, 6 instead of 1, 2, 3, 4, 5, 6. So we shouldn't be iterating over lines exactly, we should be iterating over the spaces in between the lines. Here, line filled in. Line I guess one way we could think of this is that when we compute this line, we're actually counting what's on top. With this line, we're actually counting what's on top again. So this extent here should still count, right? But then why won't... So is it just this whole should be +1 here? 6, 6? No, now we have an extra 6 there. Have 6, which is correct, 6. But then here we also have 6. Why is this a 6? No, the first line, we're getting screwed over by the first line here. So are all of the other lines correct now? We have 6, 6, then 2 4s, then 2 4s, then a 6. Yep, okay, so this is just wrong. So this is incorrect. We have 6, 4, 4, 4. We could brute force this a bit in a different way. We could take every single square on our grid, which there aren't that many squares, and then cast a ray towards all the sides and then see if we're inside or outside the whole shape, which we can compute fairly easily by counting the number of edges we intersect whilst casting our ray. But, ugh. It does, however, give me an idea. But like, what if we iterate from the left and then count the number of edges we've seen so far? So basically we go from the left and then count the number of vertical lines we've seen. So here we see one vertical line, so this is all inside, then we see a second vertical line, so this will be outside. Or a better example is here. Or here, we see 0 vertical lines, so these are outside, 1 vertical line, so we're inside. Here we see 1 vertical line, so we're inside, 2 vertical lines, so we're outside. And if there was another little peninsula here, then we'd have seen a third vertical line, so this is inside, and then this is outside. This is a different algorithm than what we've written so far, though. We go for that instead. Or can we fix our current thing, which counts positions? Let's go for that. That's also more correct in general. What's the data structure that we need for that, though? For that, each row we need to know all of the vertical lines that go through it. Each row we need all the vertical lines that intersect that row in order of x. This doesn't look right, does it? Yes, our graphic is wrong because our edges aren't width 0, they're actually width 1 cell. Okay, so this is just wrong. We were reasoning about this incorrectly. Let's draw the correct thing. Okay, is this correct? Because we've made mistakes before. So there should be 5 spaces there, then 3 threes. 5, then 3 threes. Okay, then 1, then 3, then 2. 1, then 3, then 2, and then 4. 4. Okay, this is about right, except our grid also has to go to 1 extra. All right. Now, we have to compute how many spaces there are inside. We computed completely wrong things. We computed 6, 4, 4, 4. When it was actually 5, 3, 3, 3. Oh, that's interesting. Are we off by 1? Then we have 1, 3, 2. 1, 3, 2, and then 4. Okay, so we're just off by 1. Why are we off by 1? We are off by 1 because we're doing this incorrectly here. This subtraction. It's next minus previous minus 1. This is correct. We now have 24. But we have to count the edges as well. That's annoying. We have to count the edges as well. First off, do we actually have 24 things on the inside? Must have, because computers are good at addition. Now, how many edges do we have? We can just sum them up, and we just have to be careful not to double count the points where they intersect, because every edge starts and ends at the same position as the previous edge, or as the adjacent edges. Right. This is this. Let's now do 10. Happens if we run this on full. Get this large number. Is correct. It's not the right answer. Your answer is too high. Too high. Let's draw the whole thing and see what we're doing wrong. Actually have a little wavy thing. Let's make a little example that has a little wavy thing. And then draw it out and see what we get. So how does this look like? We start with R, then we just go 2. Then we go down 2, right? Or down 1? Let's go down 1. Then we go right 2 again. Up 1. Check here. Let's go down 2, then up 1, right 2, and down 4, let's say. Let's look different. Then left 6, presumably. Up 4. What does this look like when it's drawn out? Realized I can move this. I can just this down to the visualization. So no, we don't want it for the visualization. Okay, so 2. Sorry. Right. Now we have our little wavy bits. Now we call our little function on this. Let's see what we get. So line by line, I have 0, 1, 2 on the first line. 0, 1, 2, that's correct. And then the second line should be 0, 3, and something. 0, 2, and then 4, 5, 6. Yep, that's 0, 2, 3, 4, 6. Now here, let's do an IO inspect and see what we computed. Zero, 2, 5, 0, 2, 2, 5, 5, 0. So 0 on the first line, yes. 2 here. Right. So we're failing. We need to compute pairs here. That's what we're doing incorrectly. Then this one is actually 2, and these ones are 5, but this shouldn't be 2. This should be 1. Here, line filled in. Say this one is false. Let's put the false before 0. Doesn't matter here. Now here. Are we inside? If this is rev plus 1, then we're the same amount of inside as we were before. Otherwise, here we've encountered an edge. Here we're going to be opposite of what we currently are. Then our total will be new total. And new total is if inside do the old thing, else total. This works. So 0, 1, 1, and then 3 zeros. Okay, 0, 1, 1. Why? Because we have to flip earlier. Right? As in, at this position, we know that this is a hole. So this hole has to be already the opposite of what it was before. Just say we start off with true here. 0, 1, 1, 5, 5, 0. 0, 1, 1, 5, 5, 0. This is incorrect. This should be 2. So what's going on? Here. We start with inside. Then we find this hole, and we add, we say 1. Good. Then find this hole. But this hole is out, we were inside here. This was true, so now we're false. So we don't count this one, and then we count nothing here. But now here. Count this as inside 1. Then we find this run here, which is the same amount of inside as before. Oh, so this is... This is technically our outside. This should be inside again. This whole line scanning thing just flat out doesn't work, does it? But it should work. Rather, the problem is that we're doing this just line by line instead of and not taking the verticals into account at all. So we can't, when we get to a spot, we can't tell whether there's an opening to the outside or not. The other frustrating thing is that we could absolutely just flood fill this, given like, this is not all that big. Definitely flood fill this. But we're not going to do that. We're going to do some computational geometry for once. Okay. So we're going to do this differently. We're going to iterate over all of the squares and check if they're inside or not. But if we do that, we might as well flood fill it. We use less memory if we do it like this, so there is an advantage. That's the plan. The plan is we take every trouble with doing the raycasting thing is that it's a lot easier when the lines, when the edges are of infinitesimal width. It's really annoying here. So what we need to do is we consider the square. Then we cast a ray in each of the 4 directions. Then we count whether we've encountered an even or odd number of edges. So counter 1 edge here, so we're inside with respect to left, we're inside with respect to top, we're inside with respect to bottom. Now here, we encounter 1, 2, and 3 edges, so we are inside as well here. However, here, we cast the ray up. We cast the ray up and we see 0 edges, so we are outside. And also, we cast the rays to the sides, we get even number of edges on all the sides. How about here? We get an odd number of edges top, then we get, yeah, this. This is annoying. We get 1, 2, 3. Get 3 edges, an odd number of edges to the side, odd right and odd bottom. Just odd. 1, 2, 3. As long as we see an odd number of edges to all sides, then we're good. Well, the upside of doing that, at least, is that we can draw it out and see how we get it wrong. Right? Given x and y, how do we know if, given an x value, so a single line, and a y, how do we tell which edges do we intersect? We check all the edges. We can just do this linearly, even though it's going to be slow. We can just focus on correctness for start. Then we check if the edge has x values. It depends if it's a horizontal or vertical edge. But we have to check whether the edges x and y sort of go around. Yeah, they have to include the y, the x. So for this square, the y values of this edge have to include it, and they do. And then the x value has to be less to be on the left-hand side or greater than to be on the right-hand side. We can do each cardinal, we can do vertical and horizontal with a single pass. Okay, and it's saying that these are the inside things, at least with respect to horizontalness. Right. Now if I run here, okay, why did this one not work? We have an odd number above and an odd number below, not counting the horizontal lines. Yes, because we're not counting this horizontal line either, so there should be only 2 lines here. X1. Square is going to be 1, 0, 1, 2. X is 3. Let's print out some stuff. Dot line dot y. It should be 4. 0, 1, 2, 3. No, 3. Line 107. X1. Y. Just want to see all of the spots on Y. So, checking 1, 3. It's multiple lines, which is the line we care about. What does it start with below and above? Awkward. So 1, 3. There's just one above. 1, 3 is above this thing. Zero, 0, 2, 0. Zero, 0, 2, 0. It's this one. It says it's below, not above. Okay. Then 1, 3 against where this is. It says 6, 5, 0, 5. 6, 5 to 0, 5. 6, 5 to 0, 5. It's this big one here. It's above this one. Okay. And it checks 2, 3 against 2 of them as well. No, against 3 of them. Checks 2, 3 against the third one. Which is the third one? This is the same as before. This is the same as before. This is the new one. This is 2, 2, 4, 2. There. 4, 2. No, but this is checking 2, 3. 2, 3. This one. It's checking it against 2, 2, 4, 2. Oh, because there's 1, 2, 3. Okay. Okay. Just going to take a wild guess and say that this should be a strict comparison here. Here as well. This actually didn't matter. Well, it did count down on the number of comparisons, presumably. So 2, 3. Checks 2, 3 against just 1 now. It should still check against 2. Oh, so it can't be a strict comparison. Strict comparison on one side and open on the other? That sounds like an incorrect hack. problem here really is that we have overlapping lines, but we don't know whether the overlapping lines define an extent or not. We don't know whether the overlapping lines carve out something outside of the shape. So these lines here definitely carve something out, but these lines here don't. Here don't. The reason, I guess, is because if we look up here, these two lines are connected by this segment here. So this is conceptually just one line as far as we're concerned, as is this. Outside. This is outside, and then now we are inside because we've encountered this line. Still inside here because although we encountered new line, we're walking down this edge. It'd be easier if we just converted our lines to reflect only the top edges rather than these rectangular things. Then we'd have literally just lines. But then track of which is the outer edge. Because the outer edge of this is 0 to 2. Then going down, the outer edge is... It depends on whether this goes left or right, or down again. Pretty close to just giving up and doing the flood fill. That at least is to right. Let's look at Wikipedia. Maybe if we can't figure this out. Side polygon. This is what we were trying to do, but this kind of doesn't work because our lines overlap. We'll just make them not overlap, right? I mean, we could just start each line, instead of overlapping the corners, not overlapping the corners. And so if we don't overlap the corners, then this is one line, two lines, which is odd and incorrect. This is one line, this is two lines, so it's even, which is not good. Widening number algorithm. Gone. Oh, this guy just literally copied this article. Lovely. Another technique used to check if a point is inside the polygon is to compute the given point winding number with respect to the polygon. Winding number is above 0, the point lies inside the polygon. Probably not going to work unless we have actual lines. None of these algorithms work as long as we have squares. Let's compute the lines, I guess. In the actual lines. Right there are the line edges. Let's have some amount of lines. Let's hide all of this debugging. Without any have our existing lines, so now we just want to compute the outer edges of these lines. Let's call it edges. To do that, we take this line, and what's the outer edge of this line? It will literally be this, right? It will be 0, 0, 0, 2. 1, 2. No, it will be to 0, 3. So we'll have to add 1 to the far edge. Then we go down. Down. easier to compute based on the instructions, won't it? So we start here and then we go left 2. We go 1, 2. So it's always len plus 1. Then we go down 2. Len plus... Okay, it's only plus 1 because we didn't change direction. It's plus 2 and we get here. Then we go down here. We just have to keep track of which is the outer edge. So here, which is length 2. So somehow, let's suppose we get this point somehow. Then we have to go left 6. Then we just go left 6. This feels doable, but I'm having trouble actually imagining how it look like. Part 1. Here we have this. Now we do something with edges. Now we do something with the instructions. We're just going to walk over these. This is going to be another scan. We start at 0, 0. Get a line, get an instruction that has a deer and a len. For a second, assume we don't have consecutive directions in the same. We don't have the same direction repeated. We probably don't, right? Let's assume we don't, and if we do, we can easily fix that. Then this is going to then do case there. 2. So this gives us, let's flip the direction since, should we? Let's do it like this, okay. Don't have a 0, 0, but let's assume we add a 0, 0 later. So then we have 3, 0, have 3, 3, 3, 3. Okay, this is wrong. Why? Because it's sort of wrapped back in on itself. This was a wrap towards the... this was sort of a concave and this was convex. Or rather, this was winding clockwise This was winding counterclockwise. Assumes that let's go right, right? Example look like it starts with a left. So the left, that one's going to be different. This is a left and then a down. This one is a counterclockwise thing. Only clockwise for now. See what we get. Then we have a down. Go right and then we go down. This is a big edge. But if we go, say, I have an example here, but if we ever went down and then left, still be a big edge. Hill. This direction. Then this direction is like this. Question is, do we add or not a 1? Say offset is nil, then it's 1. Else. Previous direction going to this direction. Right, we're basically describing the angle made. So this is a 90-degree angle, but this here is a 270 angle. We're describing the angle on the inside of. Right, so let's call this angle. No, it is previous direction. Here is a cond. Yeah. Skip the 1. Now what are the other cases? The previous direction also a case. Case there and there. So nil and anything is a 1. However, if we have left, now if we go right and then down, this is also 90-degree angle. However, if we went, say, right and then up, zero. We were going down and then we go left. So whether it's on the outside or not, doesn't it? This is 1. We go down to the right. This is 0. We go right. Sorry, if we went previously left. Now we're going up. This is a 1. This does not feel, what I'm currently writing does not feel right at all. Previously went up, and then we go right. It's a 1, otherwise it's a 0. Always have to return there as get 0 right. Then we get 3, 3 down. 1, 2. That is wrong. Why? Because if it went down and right, down, this is also delayed by 1. Right, we care about the next direction, not about the previous direction. Okay, instead of a scan, let's do this like this. Enum chunk by chunk every 1. So this should give us pairs of instructions. Yes, and then they repeat. Now, here, start at 0, 0, and that's it. Then we take 2 arguments. Take a list here. Then we also have next here. Don't have this prev there business anymore. Then we don't have to return there anymore. Here. Have there. Next there. So if we have right and down, then we add a 1. Otherwise, see if this is right. False. There. Do this. Discard. Turns 3032. 3032. And the next one should be 42. 52. Why? Because it went. It went down and right. 0. This was emitted by 3.0. This was emitted by 3.2. That's correct. But now here we have this one. We go right and then up. Go right and then up. It should be 0. Let's say 5.2. 0, 1, 2, 3, 4. Because it pointed this thing out. Right, so this isn't right. This is not right at all. Should be doable. We are at 3.2. Is 3.2 correct? 0, 1, 2, 3, 0, 1, 2. So we are at 3.2. Now we have an instruction that says go right for 3. So it says go right for 2. Right for, so it should compute 5.2. 5.2, okay. The problem is that here we already we're changing direction once more. All right. What if we generate multiple lines? And what if here we actually generate multiple non-overlapping lines? Because we know that the next one, when we do this direction, we know that the next line is going to start here. So we can let it do that edge itself. Then we do this line, but then here. This one generates only one outer edge, not two outer edges. If we just did this like the really nasty way. What if we just took the instructions there's nothing forcing us to work on an integer grid. We took the instructions and just drew a line in the middle. Because that would remove the overlap and everything else would still be fine. Let's try this and see what happens. In fact, so we don't start at 0, 0, we start at 0.5 and 0.5. Don't have this offset business. Here we do. X minus len, X plus len, get these things. 2.5, 0.5. This will sort of by definition be the middles. In fact, we even have 0.5, 0.5 because it gets generated at the very end. And trivially turn this into lines by doing enum chunk every one. It's almost right, just the last one has to be 6. Last one has to be slightly different. But last one is, no, this is actually correct. This is 0.55. This one goes to the start, and then we're just missing start to this point. Here. All these points. Okay, so we have all the points now, including the last one. Let's have to pass this card here. Now that we have this, we can just do our algorithm, can't we? Can we? Just consider the midpoint and then audio, the midpoint isn't. Instead of, then we check each, say, top left corner to see if it's inside or not. But then that will show as we check all 4 corners to see if they're inside or not. Yes, if all 4 corners are inside, then the whole square is inside. Let's call these now we map this. Into a function. say edges. Definitely losing focus. Data unused. Take edges. There are edges. Where's our read input thing? Compute extents, compute edges. All right. Then here inside vertical, inside horizontal, instead of doing it on lines, we do it on edges. Should still run, but it won't quite give what we want. Code. Now it's only really checking for whether the top left corner is inside or not. And indeed, the top left. Okay, so this worked. We now need to check both top left and bottom right. If these two corners are inside, then all of it is inside. Is that correct? Let's check all four corners so that we don't have to think about it. Raycast inside. So horizontal and vertical. So we're going to do 4. Offset x is 0 to 1. Offset y 0 to 1. Do. Really wish, like, writing a lot of code like this makes me wish for a better editor. The Livebook thing is just really not up to it. Not up to writing lots of code. Yeah. Inside, want one of these. But instead of x, it's x plus offset x, y plus offset y. And side vertical. And if all of these are true, it would work to pipe something into if. True. Parser didn't fail. This output something. Okay, and those are actually the inside things. Let's not inspect anymore. Just try what happens if we do this on example. Okay, that looks right. What happens if we do this on full? Takes a really long time for starters. Does it take a really long time? Because we're very much not optimized. And then it didn't actually draw anything because, of course, our squares are just not big enough. How can we actually make this draw? Two seconds. Let's this into a bit of code so that we don't hit it multiple times. This here is now data. Then here, just get rid of these. Let's color the rectangles completely. Now this will execute for 20 seconds, but then hopefully have this graph with all of the inside colored in. This kind of looks right. Okay, so let's suppose that this is correct. This means we now have the set of inside, which is everything that is completely inside, but we do not have the edges yet. But we do have the edge computations somewhere in here. Compute edges. This is it. Oh. Compute filled in edges. This is the computation that we need. This takes lines. Let's run this on their example first. So we have some number of things inside and also filled in edges, right? No. Need to do part 1, filled in 38. Here, then data dot filled in edges plus set dot size of data dot inside 62, which is 62 is correct. What happens if we do this on example 2? 37. So we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. Right? What happens if we run it on full? This will again take 20 seconds to execute. The result should be less than this, because this was too high. Oh, this is definitely a smaller number. 35,991. 35,991. Oh god, that's the right answer. You are 1 gold star closer to restoring snow operations. This would have been so much easier if I had just done the bloody flood fill on the grid. But no, I wanted to do computational geometry. Let's see if the bet paid off. If part 2 is something that can be solved with a grid operation, then this was wasted effort. If it required some computational geometry, then it wasn't wasted effort. Part 2. The elves were right to be concerned. The planned lagoon would be much too small. After a few minutes, someone realizes what happened. Someone swapped the caller and instruction parameters when producing the dig plan. They wouldn't have time to fix the bug. One of them asks you if you can extract the correct instructions from the hexadecimal codes. Each hexadecimal code is 6 hexadecimal digits long. The first 5 hexadecimal digits encode the distance in meters as a 5-digit hexadecimal number. The last hexadecimal digit encodes the direction to dig. 0 means R, 1 means 2 means L, 3 means U. So in the example, the hexadecimal codes would be converted into true instructions. God damn it, these are really big numbers. Digging out this loop and its interior produces a lagoon that can hold an impressive something cubic meters of lava. Convert the hexadecimal codes into the correct instructions. If the elves followed this new dig plan, how many cubic meters of lava could the lagoon hold? Right, so we can't do our thing anymore because we cannot iterate over this massive grid. So how do we compute the area of a polygon algorithm? Surely this exists. Shoelace formula. Here is the standard method. Sum the cross products around each vertex, much simpler than triangulation. Looks really simple. Assuming a series of points in 2D that do not self-intersect, what is an efficient method of determining the area of the resulting polygon? The only slight problem with this is that we actually have our lines are the lines on the inside, are on the inside of our little edges. So our lines are something like 0.5 to. Our lines are not integers. Is this the shoelace formula? What's this? The shoelace formula, also known as sure polygon area formulas. Okay, so yeah, this is the cross products the Stack Overflow answer mentioned. Did this fairly easily. But for this, we need to not cut corners. Here, we are currently determining our edges to be on the inside of these blocky outlines. We should do this, we should figure out what the outer edges are. Outset once. Is outset a thing? Set operation. Not outset. Set of a polygon. The Mildred offset one using its straight skeleton. Have a number of self-section described as an array of boundary points. Let's draw out our edges so that we can then debug it when it inevitably doesn't work. This is the edge we currently have. I want to outset this by 0.5. Start writing a function to do this. We're going to put it here and then we're going to put it later somewhere else. This is just going to return data with some updated edges. Take all of the edges and do something with them. I think the bits that matter are two edges surrounding each edge. Right? Yes. Okay, so here, edges, let's call these new edges. Out edges. Chunk every one. Is this a thing I can actually write? This gives me the first edge. This is the second edge. Edge is not found. Right. Okay, so the first one here is going to be the second edge. It's 2525. So it's 2505, one going down to 2525. It's this one going down to this one. And it shows me the previous edge and the edge afterward. Right. What's the last edge that we see here? So the last full triplet is the one in the middle. This is 6555. So 6555 is this one, and then it goes all the way to 5505. This one. So we're missing this edge. Take the first edge and add it here. Yes. Can we add something at the beginning? We can add the last edge at the beginning. So in edges, we're going to dot past at edges runs with this. We pass discard. Okay. First edge now is 0505 to 2505, so it's this edge. The previous one is 0505 and 55, so it's this one. Okay, and our last one is what? It's 6555, so it's this one, going all the way to 0555, this one. Okay, so now we have our triplets. Now for each of these, the question is, how do we outset? This point here, for example, we have to outset it like this. But do we know that it has to be like this? This one gets outset this. This one gets outset also like this. But that... Okay, so the rule isn't triplets. I was wrong. Something else. We need to know which is which side of each. Right, we need to know for each edge which side is the inside and which side is the outside. Oh, we can actually do that, can't we? Yeah, this is going to be easier. So we need to know which is inside and which is outside, and then we always inset towards the outside. So here we know that the left side is the inside. Sorry, the right side is the inside. Oh, and for once it's actually going to be helpful that we didn't sort the coordinates earlier. We've been running into problems with that so far. But now it actually matters, because we know that the right side here is the inside. Okay? How does that help us? So this edge here, let's get rid of this triple thing. Right. This is our first edge. So we know that inside is on the right. This is a horizontal. We know that this is a horizontal because y is unchanged. So we have to increase. So we go up, we expand towards the left, which means we expand towards the negative y and towards both positive and negative, both negative and positive x. Then the next line is going to be this. This is a vertical line. We know that the inside is on the right side. Since the inside is on the right side, we have to expand towards the left. Towards the left, in this case, is going to be positive x. Why is it positive x? It's positive x because we're going towards positive y. And here it was negative y because we're going towards positive x. Let's try this out and see what happens. But we still need the other edges. Right, because if this had gone left and up, then we'd have had to extrude, we had to outset towards the going down. So we outset opposite from edges that connect. Right? No, because you can also outset toward the edges that connect if it's sort of an inside-y peninsula thing. This isn't necessary. So we know how to compute the surface area of inside the red. We need to compute also the surface area of a little bit outside of it. The problem is that the red doesn't completely bisect our walls. Right? Because here we have 3 on the outside, then 2, but then here we have only 1. Maybe it will just be outside divided by 2. Right, let's just try writing the shoelace algorithm and see what happens. Okay, 24. Now I think I just want to add the edge. The edge is over half. Where is it? Did I call this function? Compute filled in edges. Here we go. Compute filled in edges. Filled in edges now. Filled in edges is 24. So that will give us 36, not 37. Always off by 1. We do example. Shoelace is 42. So 50, 80. But the correct answer for the example was where? 62. Huh. Oh, right. Edges divided by 2. So this is 19. 51, 61. Okay, that's suspicious. This is actually correct. Then get the output dot shoelace plus data dot filled in edges divided by 2 plus 1. Right, I can't draw this. I have to inspect this. This is 62, which is the correct answer. For example 1, it's 62, right? Yeah. For example 2, it's 37. For full, seconds. So example 2, this was 37. If I run this on full, it should give us I'm even running Raycast inside here. Yeah, this is just wrong. So on full, should return something even without the Raycast, and it returns 35991. 35911, which is correct. Okay. Okay, so we now have a better solution to part 1, a much faster solution. So let's move shoelace to part 1 and then munge our data into the part 2 format. I'm going to delete so much code at the end of this. So much code. All right. Now shoelace is in part 1. Here, we don't need to cast Raycast inside ever again. We do, however, need to do some... We also don't need this pre-computation anymore. Now here we can just do part 1, example. And then it's not, the shoelace isn't in this, it's in part 1. Then we also need compute filled in edges, and then we need this. This for as the surface. We're just going to stuff this into shoelace. Both edges and filled in data. Filled edges. This thing is going to be called area. Shoelace 2 divided by 2. It's filled in edges divided by 2. And the return value of this is area. So read input, compute filled in edges, part 1 shoelace. And here we just output area. Just make note 35991. Correct. Okay. Example. Yep. Example 2. Yep. Right. So this is correct. Now we do part 2. Finally. Part 2. This one is almost the same as part 1, except the read input function is going to be different. F module, part 2, 2. F read input. Pretend we don't see that huge error above. No idea what's causing that. Start with. Right. Copy paste our big ass input function and then we do something different with it. We take this. Put it here. These ones are now part 1. I bet we don't need to compute edges anymore. We'll deal with that later. So part 2, read input. Example. This outputs something. But now we need to parse input like this. Oh, so we're just going to ignore everything except for the color act. And 6. The first 5 hexadecimal digits include the distance in meters. Okay. So here. We don't need len, we don't need here. Or at least not directly. And column, we're just going to split a color. This is fine. There. Instead of a binary size of 7, we're going to have, when we have a hash there, this is now 6. First 5 of these is going to be, what are we calling this? This is the len. The last one is just one character. Right? It's first 5, and then the last one is the direction. And then the len becomes to integer len at base 16. And then the dir is 0, 1. So 0 means right, 1 means down. 0 means right, 1 means down. 2 means left, 3 is up. Means left is up. Was matching 48. Right, these are characters now, not strings. We'll need the color. We'll kind of want the color. Sure, why not? We're using the color in one of the display functions below. Just have it. Okay. Are these the right instructions? This instruction is right 461937. 461937, then down 56407, down 56407, and the last one is going to be up 500 to 154. Up 500 to 154. Okay. This is correct. Now we can just call these things and it should give us the right answer. For example, gives us this 952, 952, and ends in 115. Ends in 115. Okay. Cool. Is this the right answer? Oh God, yes, that's the right answer. 3 hours and 40 minutes. There were so many false starts here. Okay, now let's delete all the crap that we don't need, because there is so much crap that we don't need. Start off, we don't need compute edges here, right? We do need compute edges. But there's something we don't need. This input. Lines. Or are we using the lines to display stuff? Using lines. We're using lines to draw the outline. Okay, so let's skip lines. Then let's just delete the extents we're using. Compute line by line. This is definitely not being used. Compute filled in. Also not being used. Right? Yes, still runs. Okay, compute edges we are using. Raycast inside. We're not doing raycasting anymore. I mean, it worked, it was just way too slow. Okay, still works. Line filled in. Line filled. I can search inside of the Livebook thing. Can I? I don't think I can. Hash? Okay, just try removing it and see what happens. Runs. Does this still run? Yes. The visualization still run? Wrong. Right, we need compute filled in edges before shoelace now. Don't need this thing. Okay. We don't have inside anymore. because we can't actually draw what's inside without it. Where is it? We can't draw what's inside without the actual raycasting. I think that's it for the refactoring. We need the extents for the drawing, the lines to draw the outline. Input reading, we're going to leave it as it is. Filled in edges, yep. Edges, again, we need. And the shoelace thing. That's it. How are the stats looking like for today? Oh, 10,000 people solved it. But it's late. A lot more people should have solved it by now. I wasn't the only one who had trouble writing this. Shoelace. Okay, so review. The parsing, today's problem was just compute the inside area of a polygon. The trickiness was that our polygon was defined by walls rather than by edges. I had several bad ideas on how to solve this. One of them was basically scanning the lines to see what's inside and what isn't. That just didn't work. Then we tried raycasting against the walls. That also didn't work because the walls sort of overlap in corners. Then we finally figured out that we can just generate an edge like this through the middle of the wall, and this let us do the raycasting properly. However, the raycasting was way too slow, the raycasting was slow for part 1, and it would have never completed for part 2. So instead, we learned about the shoelace algorithm, which gives us the inside surface of a polygon. In our case, we used shoelace to compute the surface area of this red polygon here that goes through the middle of each wall. We then figured out that the outside here, the bit that's outside of the red polygon, but is still inside of the walls, is just the surface area of the walls divided by 2, which makes sense because, the red line bisects the wall, so really the surfaces are going to be half and half. And this worked. This was really fast. And this is a really neat way of computing the surface area of a polygon. Yeah, I'm going to remember this shoelace algorithm. Okay. That's it for today. Thank you for tuning in, and see you tomorrow when we do the next day, when we do day 19.